Today we're going to do a review of exponent rules that are useful for intermediate microeconomics and also a lot of other fields. But I know that we all know these rules, but there are some little details that need to be reviewed from time to time. So I'm going to go through a bunch of examples and little rules very, very quickly here. Now, we all know with exponents that if you take x times x, that equals x squared, right? And we know that if you have x times x times x, then that equals x to the third power, x cubed. Now, what sometimes we forget, because we don't do this a lot of times, is that 1 over x is the same as x to the minus 1. X to the negative 1 power, or 1 over x squared, would be x to the minus 2 power. Now, when it comes to simplifying exponents, there are a lot of rules that you need to keep in mind. Now, one thing I just want to point out, that if you have something like x cubed plus x squared, that you cannot really simplify that. Because you have x's to the different powers, you can't make that into the x to the fifth or anything like that. However, as we should remember, if you do have two things that are the same power, like x cubed plus x cubed, that's going to give you 2x cubed. Pretty straightforward there. Now, on the other hand, if you have, say, x cubed times x squared, what is that really? Well, what that is really saying is you have x times x times x, that's x cubed, so x times x times x, and x squared is x times x, so what you end up with here is 5x's, which is x to the fifth. Now, you can see that's x to the fifth. The rule that you should keep in mind, what sometimes we call the law of exponents, is that if you have x to the third times x squared, you add the exponents together. So that gives you x to the 3 plus 2, or x to the fifth. And this is a general rule that you can always use to simplify, as long as you're talking about x times another x to any exponent, you add those exponents together. Now, on the other hand, if you have an x, say, cubed, and then you want to square that, what does that give you? Well, to square something is to multiply it times itself, and so x cubed squared is just x times x times x, which is x cubed, times x times x times x, right? And so you've got x to the sixth there. Now the rule is, if you raise an exponent to another power, you multiply those exponents. So x to the 2 times 3, x to the sixth. Now, what about square roots or powers less than 1? Well, a square root of x, if we remember this law of exponents, if we know that the square root of x times the square root of x is equal to x, and if we're going to add the exponents here, because they're multiplied by each other, what we must be adding together is a half plus a half to get x to the first here. And so that's a way of seeing that the square root has to be the half power. So x to the 1/2 times x to the 1/2. That's just a different way of writing the square root of x times the square root of x equals x. And a numerical example you can really clearly see is 3 times 3 equals 9, right? 3 is the square root of 9, 3 is the square root of 9, multiply them together and you get 9. What about other kinds of roots? What about a cube root that sometimes we'll write like this? A square root sign with a little 3 up there. What do we do with the cube root of x? Well, the cube root of x is the same as x to the 1/3 power. Why? Well, because we know that if we take x to the third times x to the third times x to the third times x to the third, and we add those exponents, we get a third plus a third plus a third equals x to the first power again. So the cube root is the same as the 1/3 power. And you can generalize this idea to any 1 over power that you want, 1/4, 1/5, or 1/100th for that matter. So the 100th root you could write as x to the 1 over 100. So just like just one more example here, I'm probably beating this horse to death, but the 7th root would be of x, we could write as x to the 1/7. Now, what if you had something like this, x to the 0.375? What in the world is that? Well, x to the 0.375, that decimal is a representation of x to the 3/8. 3/8 is the same as 0.375. What is x to the 3/8? What does it really mean? Well, you can write x to the 3/8 this way. You can write it as x to the 1/8 times x to the 1/8 times x to the 1/8. Because of that law of exponents, it says that if you add 1/8 plus 1/8 plus 1/8 together, you get 3/8. So we must be able to write x to the 3/8 as x to the 1/8 times x to the 1/8 times x to the 1/8. But what's a simpler way to write that? It's x to the 1/8 cubed. So anytime you have a power that is a decimal, as long as you can write that decimal as a fraction, you can, and any either repeating or decimal that stops like this, it is possible to write it as a rational number, which is just a fraction. So you can understand what any kind of decimal exponent means in this kind of way. Now, this can generalize. So now that we understand what a fractional exponent means, we can use that law of exponent in just exactly the same way if we have x to the 0.3 times x to the 0.4 to add the exponents, 0.3 plus 0.4, x to the 0.7. So no problem. But let me just expand this out, just to make sure we really understand what's going on. X to the 0.7 is what? Well, x to the 0.7 is x to the 7/10, which we could rewrite as x to the 1/10 raised to the 7th power. And if you don't see why, go back and look at this example right above it, and you'll see exactly why we are allowed to do that. Now, let's calculate some numbers just real quickly so that we can make sure we have a good grasp of where we are at this moment. So let me go back up here. I've still got a little bit of space. So what if you were working with numbers and somebody said, okay, well, I know I have this equation, x to the 0.7 equals 5, and you wanted to solve that for x. What would you do to solve that for x? Well, there are a few options. Now, one thing that we can do is to take both sides of the equation, just like any kind of algebra. If you want to solve an equation, do the same thing to both sides. In order to get rid of this 0.7 exponent, we need to raise it to the inverse of 0.7. That is, if we take x to the 0.7 and we raise it to the 1 over 0.7 power, and then we do that to the other side, 5 raised to the 1 over 0.7 power, then x is going to equal whatever 5 to the 1 over 0.7 power is. Now, if we had a calculator, how would we actually do this? Let me give you two methods. Method number one, it would be to take 5, because 1 over 0.7 is the same as, we can rewrite that as 10/7. So one way to solve this would be to rewrite it this way, and then realize that 5 to the 10/7 is the same as 5 to the 1/7 raised to the 10th power, and then just do these operations separately. Raise 5 to the 1/7 power, then raise that answer to the 10th power, and you'll get your answer. Another way that you can do this is to simply calculate this value, 1 over 0.7. And if you take 1 over 0.7, and we want to raise 5 to that power, that's the same. 1 over 0.7 is approximately 1.4828571429. So we could raise 5 to the 1.4828571429 power, and that will give us our answer, which is approximately 9.966. So the general rule or the general idea is for any equation that you have, x to any exponent, anything, we'll just call it n, x to the n power, whether n is a decimal or a fraction or a whole number, if you have x to the n equals 5, in order to solve that equation, raise both sides to the 1 over n, right? So just raise this side to the 1 over n, that'll give you x. Raise this side to 1 divided by n, whatever n is. So if n is 2, you're just taking the square root of both sides, 5 to the 1/2 power. Now, just like some of the examples above, we can deal with decimal exponents exactly the same way, just to make sure that we're clear on that. What if we take x to the 0.2 times x to the 0.4? That can be simplified to simply x to the 0.6. We just add those exponents as we usually would. Now, what about dividing? Well, dividing, instead of adding exponents, you subtract exponents. And here's where this rule comes from. Suppose we have x to the 4th over x, or x to the 1st. Well, we know that's the same thing as x times x times x times x over x. And what you might think about doing is, well, we're just going to cancel those two x's, and what are we left with? Well, we're left with x to the 3rd. Well, the rule of exponents says we don't have to go through all that. It's good to know that's what's happening, but really what we're doing is taking the x to the 4th and we're subtracting 1, because we have a 4 on the top and an exponent of 1 on the bottom there. Now, the same exact principle works if we have decimal exponents. So let me move down to a new page here. If we had a situation where we had x to the 0.4 divided by x to the 0.1, it's exactly the same. We subtract those exponents and we're going to get x to the 0.3. And we already know how to handle that. Now, what if we had a situation where the exponent on the bottom was bigger than the exponent on the top? For example, suppose we had x to the 0.3 divided by x to the 0.5. You can still do exactly the same thing. 0.3 minus 0.5 equals minus 0.2. That's just x to the minus 0.2. And as we saw up above, that is the same as 1 over x to the 0.2. So nothing really mysterious. As long as you know the rules and you stick to them, you won't have any problems. So just a couple of more things here that you need to see in order to make sure that you're really clear on how to handle situations with exponents. What if you saw something like this, where it's x to the 0.2, y to the 0.6, times, so that's in parentheses over here, and that was times x to the 0.1, y to the 0.1, for example. Well, since everything's multiplied and nothing's added here, all you do is just add the exponents with the x's and add the exponents with respect to the y's. So you'll end up with x to the 0.3, y to the 0.7 here. Nothing real tricky. And you can do the same thing with division. What if we took this exact same example here, and instead of multiplying, I just drew a division sign through those two things? Well, then we would subtract the exponents. And instead of x to the 0.3, x to the 0.7, we would say x to the 0.2 minus 0.1. Well, that's going to give us x to the 0.1. 0.6 minus 0.1 for the y exponent, y to the 0.5, or the square root of y in that case. Okay, one more little lesson or reminder before we get to the coup de grace, the most complicated kind of exponent situation that you see in intermediate microeconomics. Let me remind you how to divide a fraction by a fraction. If we have, say, a fraction 4/5, all divided by 2/3. How do you divide 4/5 by 2/3? Well, the rule there to remember is invert and multiply. So what we do is we take the 2/3, bring it up to the top, invert it, and make it into 3/2, and multiply those two fractions. So how do you multiply a fraction? You multiply across. 4 times 3 is 12, and 5 times 2 is 10, so that's just 12/10, or we could reduce that to 6/5 if we wanted to, and that's just the same thing as 1.2. But what if we have a complicated situation with exponents? All we have to do is combine all the ideas that we've seen already, and it's not going to be a problem at all. So here's the most complicated thing you'll see, but after you see how this is done once, you'll be able to handle it. What if we have something like x to the point, well, let me change that there. Let's do y to the point 3 over x to the point 6. That's one fraction divided by another fraction, say x to the point 3 divided by y to the point 7. All we have to do is combine all the ideas that we've already seen before. We're going to take this fraction on the bottom, invert and multiply it. So we take the y to the point 7 on top, divided by x to the point 3, and now we multiply across. Y to the point 3 times y to the point 7 is y to the first, divided by x to the point 6 times x to the point 3 is x to the point 9. And if you understand all these exponent rules and practice them, there's no kind of situation with exponents that I think you won't be able to handle.